Number 37, we have an improper integral from 0 to 2 dx over the square root of 4 minus x squared. The actually correct notation would be to write this as c approaches 2, or whatever letter, if you use A or B or C here, that's fine. From the minus, because you're going from 0 to 2, that means you're going this way on the number line, so you're going, and in limit terminology, that's the minus direction, left to right. So we evaluate this from c to 0, and that's a pretty easy integral. It's just straight up arc sine of u over a. So it's arc sine of u over a, x over 2. Of course, square root of 4 is 2 there, not this 2, it's the square root of 4. Put in c, put in 0. So we only need the limit part wherever we have the c. So it's a limit, c approaches 2, negative sine inverse of c over 2. You put 0 in there directly. Sine inverse of 0 is 0. So you plug the 2 in there. You have sine inverse of 1 minus 0. And sine inverse or arc sine of 1 is pi over 2. So therefore it will converge to pi over 2. 38. Let's see, this is an infinity limit. So limit b goes to infinity from 10 to b, x minus 8 to the negative 1/4 dx. So that's a pretty straight up just u substitution problem. Not too complicated. So you will apply the power rule to u. I didn't write it out here, but the antiderivative of u to the negative 1/4 would be 4/3 u to the 3/4. So then I substituted back the x back in there. And put in the b, put in the 10. And what do we have? All right, well, you get a real number over here when you put the 10 in there, but here it fails right there. So you have limit of infinity going to the 3/4 power is going to be infinity. So diverges when you get infinity. Now here's one with negative infinity as a limit, lower limit. So we're going to let limit as b approaches negative infinity from b to 0. I just brought this up for substitution purposes. You could have left it on the bottom and then brought the power up. But x minus 1 to the negative 2 is just going to be u substitution. And I didn't even show the u du, but u would just be x minus 1. Du would be dx. So the antiderivative of u to the negative 2 would be u to the negative 1 over negative 1, which just makes this 7 divided by negative 1, so it makes it negative 7. All right, now now I went ahead and dropped it back down here. So I put 0 in there, and that's going to give me 0 minus 1 is negative 1 raised to the negative 1. Well, that's just 1 over, basically it's just 1 over negative 1. So it's negative 1, negative 7 times negative 1 makes positive 7. And then when you evaluate this part here, you see it's 1 over b minus 1. As b goes to negative infinity, that's still going to go to 0. So this part zeroes out. And we have 7 minus 0, so our integral converges to 7. Now we're starting with some sequence terms here. So let's see what we got here. This is a recursive sequence. And you have to be depends on how many prior terms you're using. If you're only using one prior term like we are here, you only have to be spotted one term up here. If we were using 2 prior terms, I'd have to have S1 and S2 defined here. So starting when n is 2, Sn is going to equal n divided by n plus 3 times Sn minus 1. So n will be 2 the first time. Now you see that all the answers have 4 for the first term. It'd be kind of silly for them to put any answers that didn't have 4. Because it's pretty much telling you right here that S1 equals 4, so the first one's got to be 4. So I put 4 in there for the 1, and then I put, but the n is 2, so it's 2 divided by 2 plus 3 times 4, which gives me 8/5. So now I go to evaluate S3, and I have put in 3 for n, so it's going to be 3 divided by 3 plus 3 times the previous term. So now we're always just using the previous term, which we were the first time too. But so it's 3 over 3 plus 3 times 8/5 ends up being 4/5. So S4 will be n is 4, will be 4 divided by 4 plus 3 times the previous term we just found here, 4/5. That ends up being 16 over 35. And S5 will be n is 5, 5 divided by 5 plus 3 times the previous term of 16 over 35. And you get 10 over 35, which reduces to 2 over 7. And then answer choice B up here is the correct one that has the first 5 terms of that sequence. Going to find the limit of this sequence. Now this business over here, this n equals 1 and infinity business doesn't need to be there really, because it could say like an equals this sequence, not series. But when you're finding the limit of a sequence, my point is we're always finding it as n goes to infinity. There's no, you don't evaluate a sequence as n goes to 10 or something like that. It's implied infinity, because we're trying to see if the terms are progressing towards a specific term over time. So you line this up, now you look around on the terms out of order in the numerator, see they're trying to trick you there, so you're trying to identify the largest powered term on top over the largest powered term on bottom. We have 8n4 over 9n4. Now we don't need to do 4 L'Hopital's rules here to work this out. As long as we realize we have n4 and n4 the same, so as it goes to infinity, this sequence will start approaching 8 over 9. Now here's another one that kind of has that weird notation, but the same idea. Well, as n goes to infinity, now I used the log property that allows me to bring that 4 down. You have infinity over infinity, so technically this does require L'Hopital's rule. So I take the derivative of the top, which is 4 over n, the derivative of the bottom, which is 3n squared. I didn't go any further, but basically that's 4 over 3n cubed. As n goes to infinity, that's enough clearly to say that this was going to converge to 0 for sure. Let's take a look at number 43. This one, if you started listing out the terms like I did here, because it's kind of tricky with that -1 to the n when you evaluate that limit. It's kind of weird. There's no real way to, like, if I had like n in the denominator, then the whole thing would go to 0 or any power of n. But here, if you just list the terms out, what's going to happen is, starting with 1, you're just going to go back and forth between 1/2, 3/2, 1/2, 3/2, 1/2, forever and ever and ever. So it's never going to actually, even though it's not going to infinity, it's not getting larger and larger like a lot of sequences do that diverge. It's just because they grow without bound. Like let's say if you had, 2, 4, 6, 8, 10, 12, blah, 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 that would just keep growing and growing. This one diverges not because of that reason. It's just because it's never going to approach a certain value. It's just going to keep just changing back and forth. All right. Let's take a look at 44. Now, I'm sure on the actual, when I convert this over to this particular format, sometimes it smashes up the stuff. So I'm sure that on the actual questions sheet itself, you would see that this was actually written as 7 times 1/2 to the n. So thank goodness, we have that sheet to look at. So if anything gets messed up here, that happens from something. Yeah. So 7 over 2 to the n is the same as 7 times 1/2 to the n. We have a geometric series. Do that a couple of ways. This is the way I show it, but I'll also learn another way to do it too. But let me show you this. So this starts at 1, very important, because our formula given to us of a over 1 minus r, that's implied that you're starting at 0. So if you don't start at 0, if you start at somewhere further than 0, you still use that formula, which is the sum starting at 0, then you subtract off any term before where you're starting. So if we're starting at n equals 1, that means we want to get rid of the n equals 0 term, or subtract the n equals 0 term. So I have 7 over 1 minus 1/2, which that would be the right answer if this was 0 right here. And sure enough, answer D is what 14, no, I'm sorry, it's 14C, answer C. If it started at 0, answer C is there, so you have to be very careful with this. You wouldn't want to make a mistake, miss that on a test question for that reason. But now I'm going to subtract the term off if you put 0 in there. So that's basically 7 over 1, which is 7, so actually it's 14 minus 7, which equals 7. Another way someone showed me how to do this is if you actually put 0 in there initially and make it, so that would make it 7/2, and then you still have 7 over like 1/2 to the end. I'm sorry, 1/2, 1 over, yeah, 1/2 to the end. I just wrote it wrong, yeah. So, like so, you could actually treat, now multiply those together, and you have 49 over 2, and you wouldn't have to subtract off that initial term if you did it that way. But I believe that's correct. Let's see, what would that be? That would be 49 over 2. No, that's not right. I think this extra 7 doesn't belong here. Yeah, I think you're changing 7 to this new 7/2 by putting the 1 in there. Yeah, that would be right, because 7/2 over 1 minus 1/2 would be 7/2 over 1/2, which equals 7. So yeah, so that means this 7 is now becoming 7/2. That's just an alternative way to do it. But I don't know. I like the subtracting off the prior terms, but someone did enlighten me with that little trick, so I thought I would share it. I probably mentioned that on the video for the exam 3 solutions. All right, telescoping series. This means we'll have to do, if it's written like this, if it's already written as a fraction, we won't have to. But if it's written as, in this form, separate fractions, I should say, not a fraction. Of course, it's written as a fraction. Has to be partial fraction decomposed there. So these will always be simple, distinct linear fractions. So you see it's a over n over b over n plus 3. And so it's pretty easy. You just do that like you do a basic partial fraction. You get a 7/3 and a negative 7/3 as your a and b. Now there's 2 ways you can do this. You can leave the a and the b, the 7/3 and the negative 7/3 in the numerator of these fractions if you want to. Or you can do what I did. You just have to be careful if you do what I did, which it makes it cleaner looking. But I pulled the 7/3 out, so it just left a 1 here and a negative 1 here. Now this has to end up being subtraction. When you break that decomposition down, you have to get subtraction here, because that's what makes it a telescoping series, is it must be minus between those 2 terms. Telescoping series is always going to converge, but that's what makes it telescoping, is the minus. So just remember, we have to multiply this 7/3 by whatever we get. So if you want to build out, a few of the terms like I did here by putting in n equals 1, 2, 3, 4. So you see how the 1/4 cancel and 1/5 cancels. And what happens is these other terms will essentially fade away to 0. They'll just start getting smaller and smaller and smaller. And these terms I circled right here aren't going anywhere. They're definitely part of the answer. And I wrote a note here. That's the way I teach this in the notes, and also would have had this on probably on explanation on the videos. There's another little trick, but if you forgot this trick, that's okay. Just build this out and see how many you're going to have. The trick is the difference between n and n plus 3 is 3. So that means that's the number of first terms you're going to be left with there. It's the first 3 in these parentheses. But that's okay if you forget that. Just sort of list them out, recognize what's going to cancel, and then realize all these trailing terms there toward the end. You know, I mean, they're all going to eventually cancel, but then they're going to have three of them that aren't going to cancel, but they're going to fade away to being close to zero. So that's what doesn't matter. So like if I started another parentheses, I would have a 1 over 6, and then that would cancel with that 1 over 6 right here. So those fade away. So let's don't forget our 7/3 in front. So we have 1 plus 1/2 plus 1/3. That equals 11 over 6 times that 7/3, and we get 77 over 18. There it is. Answer D. Number 46. Determine integral test converges or diverges. Well, let's see what happens here. This integral is not too bad. It might look complicated, but it's just a basic u substitution. It looks weird, but actually when you let u equal x, you're going to get du equals negative 1 over x squared, and then that's going to make it fit that denominator perfectly. Now I changed the limits of integration on this one. Most of the time I do. I think I did one where I didn't do it on the improper integrals, but in these problems. But 99% of the time I will do it. So that we're going from 1 to b because we're replacing the infinity with b. You see we have the limit right here. So u of b will be 1 over b, and then u is put in 1 over 1, of course, will be 1. And so I'm going from 1 to 1 over b. And because of the du here being a negative, I have to have a negative. I have to adjust for that negative with the negative on the outside. I guess I made a little math mistake here by not having the dx sitting right there. Okay, but anyway, that's all right. So the negative comes out from this du right here. So now we just have cos of u du, so that's an easy antiderivative. Antiderivative of cos of u is sine of u. And then we put in 1 over b, we put in 1. So it's the negative limit, b goes to infinity of sine of 1 over b, minus the minus limit of sine of 1. Now one thing I didn't do here that I do a lot of times with definite integrals, I don't know why I didn't do it here, but I think I'll write it here so you can see it, is whenever I have negative in front of definite integrals, it's always usually my instinct to, well, let me forget this limit part, is, okay, everything's the same, is I can get rid of that negative by reversing these limits, right, reversing these. By properties of definite integrals. And I don't know why I didn't do that here. I still got the same answer, but that's usually what I do. But flip them over and get rid of that extra, and you see how we don't have to deal with all these little negatives. So what do we have then? That's going to, so 1 over infinity will be 0. Sine of 0 is 0. So you just come up with this answer converges to sine of, 1 radian basically. Well, okay, they're not worried about that, but key is it converges. All right, so let's take a look at this number 47. Oh, I guess the same instructions are integral test here. Okay, but I made a note though. I did the integral test. I wouldn't worry too much about this because you can look at my work if you want to, but the better way to do this, like I wrote here, is LCT with 1 over n. But it does diverge by the integral test, but it diverges by LCT. So they do have to come to the same conclusion. The problem with this one, you'll end up with natural log, and you have natural log of infinity, which diverges. But you compare it with 1 over n, you get a positive finite number, which you're supposed to get for the limit comparison test. That means you compared it correctly, if it could be compared. There are some things you can't, obviously you can't use the LCT for, but 1 over n is a diverging p-series, so therefore our series will also diverge. So, the instructions said integral test, but Well, this might be one on the final where it says, what ways, how can you establish divergence for this test? And we would know that even without working it out, if you knew that it could be, in other words, if you knew that it was LCT with 1 over n and it diverged, then you would also, without even integrating it, it's got to also diverge without even working it out. At least you would be aware, kind of by looking at it, that the integral test applies because it's U substitution. All right, this is let's see, direct comparison. That's kind of a weird test. It's not used all that often. We learned about it. It's really good for weird situations like this when there really is no other way to do it. But there's a lot of times that direct comparison doesn't work where limit comparison would, and sometimes they both work because it's the limit comparison. All you have to do is compare it with something and get a positive and finite number. Direct comparison is real picky about larger converge means smaller converge, and smaller diverge means larger diverge. So the order is very important. So there's some series that that would not come to a conclusion by the direct comparison test, but they would by the limit comparison test. But this is good because the direct comparison test, limit comparison test would not make any sense there. You couldn't even really use it for this one. It would not produce anything of any value. It'd be no good. But it's perfect for this because since sine is always between -1 and 1, cosine is always between -1 and 1. When you multiply them together, they'll always be between -1 and 1. So you can compare it properly with 1 over 9 to the n, which is also 1/9 to the n. That's a converging geometric series because the common ratio is 1/9, which is less than 1. So if you can clearly say that, which we can, that this 1 over 9 to the n is greater than this sine n cosine over 9 to the n, we can because we have the same denominators. Therefore, we're saying larger converges implies smaller converges. Convergences. Well, I kind of messed that up, didn't I? That's kind of rude. Converge. Too many letters. Yeah, so that worked then. Smaller converge, larger converge. Right, so okay, fix that up, and then okay, everything looks good. So it converges by direct comparison test.